There we go. That looks perfect.
Okay, perfect. Thank you so much, everyone, for being here, and thank you for the invitation. It is a pleasure to speak with the Global Flood Partnership community. My work focuses on flood mapping at global scale using multi-sensor satellite data, such as Sentinel-1 and Sentinel-2, and large-scale Earth observation data archives. And we're combining those with AI approaches, including geospatial foundation models more recently. A central question for me and for many of you here is how do we create flood maps that generalize globally, are reliable during extreme conditions, and serve operational decision making? So today I'll present some of our recent work evaluating geospatial foundation models for global flood mapping using FloodsNet, a harmonized data set of 85 flood events across all continents. And I'll focus not only on model performance, but also on the operational trade-offs and what matters for end users. So I'd like to start by asking you to take a minute to think back to perhaps one of the most important moments in your life, the moment when you're ready to make your first home purchase. You've done all the right things. You've obviously saved up for a number of years. You've done your research, and let's say you are based in the US and you come from out of state, and you settle to purchase property in a small rural community in the state of Georgia. And the exciting day comes, you move in, and the first time it rains, your property gets flooded. And this doesn't just happen once or twice, it happens every single time it rains. Now, you had no way of knowing that because Georgia, as well as many other US states, have what we call a non disclosure law when it comes to flooding. So nobody was obliged to tell you that your property might get flooded. So what do you do? What Miss Jackie Jones did, as well as several members of her predominantly African American community, was to start a grassroots organization, and they teamed up with my lab through the American Geophysical Union's Thriving Earth Exchange, and we worked together for about a year to co-create flood maps. And those flood maps that we used for their community were not only useful to validate their lived experiences, but they were also useful for them to take them to their local council and drive home the point that their properties indeed get flooded. They need more funding to cope and mitigate the impacts of those flood events, and also to understand where to place green infrastructure to mitigate those flood events. Flooding is, of course, in this case, just had a devastating impact on a small community, but flooding worldwide impacts 1.5 billion people, or about 20% of the global population is facing an increased flooding risk. And we also know that flooding disproportionately impact overburdened communities, as you can see here on the right-hand side map, with many countries across the globe facing the impacts of floods, which again impact predominantly overburdened communities. In the US, we know that about 2/3 of all declared natural disasters involve flooding, with all 50 US states experiencing flash floods. And of course, the main impacts of floods are loss of life, disease outbreak, damage to homes and other built infrastructure, as well as crop damage, which can lead to food insecurity. Just last year, 2024, which has been the hottest year on record, we've seen major flood events across 4 continents and many countries, including Vietnam, Nigeria, Central and Eastern Europe. Towards the end of the year, in Valencia, Spain, and in the southeast of the US, where I live, Hurricanes Milton and Helene had a devastating impact on many communities. And of course, satellite-derived flood extent maps as well as flood depth maps can help us by providing equitable coverage and therefore analysis of flood events. They help us by helping emergency managers, city planners, and residents recover after flood events. We can use those maps to quantify damage in terms of assets and population impacted. And of course, historical flood maps help us understand which areas have flooded in the past and are therefore more likely to flood in the future. But despite satellite data having systematic and equitable coverage in space and time, there are still certain challenges associated with mapping floods from satellite data. And some of these challenges are included in this slide, which again include facts such as flooding are ephemeral events. So unless you have a satellite that overpasses at the time of that particular flood event, you might miss that flood event. We also know that floods have what we call variable spectral signatures. So no two floods look alike, and this can be challenging when you're trying to map floods globally with machine learning or AI algorithms, because you need to have a representative global data set that will be able to generalize across space and through time. We also know that optical data, which has been one of the main sources of data used so far in the Earth observation community, can be impacted by cloud and cloud obscuration, whereas a synthetic aperture radar, while it penetrates clouds and acquires data day and night, can misclassify water, particularly in urban areas due to double bounce effects or smooth surfaces, for example. So in the past years in my lab, we used time series of Landsat data at 30-meter resolution. We used typically at least 2 Landsat sensors and machine learning algorithms. What you see here is an example from Australia's Murray-Darling Basin, which is the largest dryland basin in the world, the size about of the 4 US corner states. And you can see in the animation on the left-hand side that this allowed us not only to quantify flooding in space and time over 2 decades, but also we could put together a flooding frequency to understand which areas would get flooded more frequently. And last but not least, it also allowed us to have over 200 stacks of flood maps, which are really critical for applications that require time series analysis, such as things when trying to understand whether climate or land use change were more important in quantifying where flooding happens. Of course, with Landsat, we have a 30-meter resolution, and even with 2 sensors, we have a 8 to 16 day frequency, so we can miss certain ephemeral flood events. And in more recent work, we teamed up with colleagues at NASA Goddard, and we were one of the first adopters of their harmonized Landsat Sentinel-2 dataset, or HLS, which at the time included only 3 sensors, so Landsat 8 and Sentinel-2A and Sentinel-2B. At the moment, it includes Landsat 9 as well. And what you can see here is across 4 study regions shown in the rows, and looking at flooding frequencies for 1 sensor on the left-hand side, Landsat 8, 2 sensors combined in the middle column, and 3 sensors combined on the left-hand side column. You can see that only with the 2 or the 3 sensors combined only, we were able to detect certain ephemeral flood events. And this animation is driving home the point that, again, on the left-hand side, we have 1 sensor, and on the right-hand side, we have the 3 sensors combined from HLS to drive home the point that only with the 3 sensors combined, as you can see here, we can pick up certain ephemeral flood events. We also wanted to understand what else is important when trying to map ephemeral floods besides the temporal resolution, particularly if they are smaller in size. So what we did here, we compared how many mixed pixels, so pixels that have both water and land in them, at the 30-meter HLS resolution, were we able to quantify using PlanetScope 3-meter commercial data. And what we found was that nearly 40% of the 30-meter HLS pixel resolution were mixed pixels when comparing them to PlanetScope data. Again, spatial resolution is important in addition to the temporal resolution. However, if we were to map floods just with high-resolution 3-meter PlanetScope data, not only can it become expensive, depending on your application, if you are trying to map floods at regional or global scales, because it's commercial data sets, so definitely it costs some money, but it's also optical data, so it can still be impacted by clouds. So for example, here we map flooding during Hurricane Helene in the city of Asheville of North Carolina, and you can see before, during, and after the flood event, you can see that during the flood event, we had lots of areas that were impacted by clouds. So motivated by these findings that both the temporal and the spatial resolution are critical when mapping floods, and wanting to use publicly available data, in a recent large project funded by NASA, we're using 10-meter publicly available complementary resolution Sentinel-1 SAR data and Sentinel-2 optical data, focusing on global flood events, and we picked 5 years, which you can see here when we show number of floods per year. Those last 5 years that we're focusing on had a relatively high number of flood events. And in this project that we're finalizing this year, we're using both traditional machine learning approaches, such as random forest and XGBoost, conventional deep learning algorithms, such as a UNet, and more recently, geospatial foundation models. So what you're seeing here is an example of a flood event that happened in Pakistan in 2022. Pakistan is a country that floods very often, but this flood event in 2022 was huge, even by the standards of large floods in Pakistan, primarily due to higher than usual monsoonal rainfalls and glacier melt in the Himalayas, which led to a lot of water coming down the Indus River basin. And you can see here in the red rectangle that I'm zooming into now, this is what the flood looked like in the Sentinel-2 data, and this is what the flood looked like in the Sentinel-1 data. And this is the flood mapped by one of our machine learning algorithms. So again, a huge, massive flood event. This is an example of a flood that happened in Greece in 2018. And here we're using a conventional UNet deep learning algorithm, again, combining Sentinel-1 and Sentinel-2 data. And more recently, we started using foundation models, which are large-scale pre-trained AI systems that have revolutionized natural language processing and computer vision, and are now advancing geospatial analysis and Earth observation data. Given that geospatial foundation models are based on self-supervised learning using terabytes of satellite data for training, their main promise is that they will improve generalization across downstream tasks, such as flood mapping, increase and improve scalability and efficiency with minimal amounts of label data. But despite the fact that we have over 50 and I guess nearly 60 by now geospatial foundation models, developments for task-specific applications, particularly for operational flood mapping, are still lacking, primarily because of a lack of representative label data sets, which are still needed to fine-tune those models for task-specific applications. So to address this challenge, together with my lab, we developed a harmonized data set called FloodsNet, using both coincident in space and time Sentinel-1 and Sentinel-2 data based on 85 global flood events. And we started applying geospatial foundation models for flood mapping with some promising early results. So we used 4 existing data sets, including Sen1 Floods 11. And if they only came with Sentinel-1, we added Sentinel-2. And if they only came with Sentinel-2, we added Sentinel-1. This is the distribution of those 85 global flood events. So again, we are capturing flooding events across all continents. And again, we are complementing existing data with missing sensors. So if Sentinel-1 is missing, we're adding Sentinel-2 and vice versa. And we're also adding layers such as the permanent and seasonal water that was derived from the Joint Research Center Global Surface Water Dataset. And this is an example of what the dataset looks like. This would be what we call the ground truth map. This is the permanent water layer. This is the flood besides the permanent water layer. This is what the flood looked like in Sentinel-2 data. This is just the water index, and this is what the flood looked like in the radar data. In terms of the geospatial foundation models, we used one of the latest geospatial foundation models, TerraMind, which was released earlier this year by IBM and DISA Phi Labs. And we used TerraMind because it's a multi-sensor, so it was trained on both Sentinel-1 and Sentinel-2 data. And it also achieved state-of-the-art performance when benchmarked against Pangea, which is a community standard benchmark for EO data. And we used the TerraTorch framework, which provides basically a flexible fine-tuning framework for geospatial foundation models. We used 4 model configurations, so 2 based on the size, the number of parameter that the model was trained on. So a base model with 103 million parameters and the large model with over 300 million parameters, and we used two backbone training modes, frozen and unfrozen. So in the frozen backbone, the backbone's parameters are kept fixed during training on any specific task, and only the additional layers on top, the task-specific heads, are trained, whereas in the unfrozen model, all the backbone weights are trainable. And we compared this using our FluxNet data set, so training it on our FluxNet data set and testing it both on the test from the FluxNet data set versus the Sen1 Floods 11, which is the default data set that was used in Terramine. So it has TM from Terramine default to show you the results. And I'll go through these tables. There'll be a couple of slides that look pretty much the same in layout, but basically we're comparing, again, Terramine tested on FluxNet versus Sen1 Floods 11, compared to the Terramine example, which was both trained and tested on Sen1 Floods 11, which is included in our FluxNet dataset. And I'm showing three accuracy metrics: the overall accuracy, the precision and recall across all of these base frozen, base unfrozen, large frozen, large unfrozen. So we can see that Terramine trained on FluxNet performed better in general in terms of overall accuracy and precision than on the Sen1 Floods 11 Terramine default example, which achieves slightly higher recall. Now, just as a quick reminder, recall is the equivalent of omission error. So basically how many floods, so missed floods, which is really important when you are an end user and want to decide whether you want to send resources to tackle the impacts of flooding. So while both precision and recall are important, typically we tend to think of recall as being more important when we talk about flooding. We also found that the best balance was achieved by the base unfrozen model because it had strong performance across all the three metrics. However, the best recall was achieved by the large unfrozen model in terms of about 2 percentage points, but it did take a lot more resources to be able to train that particular model. We also found that unfreezing the backbone improved performance, but not significantly. And we also found that the larger backbone does not consistently outperform the base. So here are some results of our predicted maps. So again, we concluded that the base unfrozen was a good compromise across the four configurations that we looked at. And this is what the results look like. So here is on the left-hand side column is a Sentinel-2 image. The ground truth mask is on the second column, and the predicted masks are on the right-hand side column. And you can see that we achieved reasonably good results using this base unfrozen model. And so, of course, those of you that are into geospatial foundation models and deep learning are probably wondering, how is this comparing with the UNet? So we compared our GFM's models with the UNet, and we found that while the UNet achieved similar overall accuracy to the 4 Terramine backbone configuration, it had the highest recall compared to all the models. So it had a recall of 93.65%, so about 2 percentage points higher than any of the Terramine 4 backbone configurations. So to summarize, why is this important? So again, it's really critical to have a large, more representative data set such as FluxNet that includes flood events across all continents. So in our case, we had 85 flood events. And it's also important to balance precision and recall. But again, I would argue that in the case of flooding, recall is really important. And we found that recall was actually higher when using a UNet and compared to those 4 configurations and using Terramine. So a couple of key takeaways. Leveraging machine learning and AI algorithms applied to satellite data is really critical for systematically consistent and equitable global flood mapping in space and time. Integrating freely available complementary all-weather radar data and optical data is important for global flood applications. Despite Landsat being what we would think of as maybe an old sensor. It's really critical for long-term time series, so it provides us with 5 decades of data. So this is, of course, important for applications that require historical flood maps and time series approaches. We found that GFMs have the potential to lower compute and data needs for training to produce accurate flood maps, but we still achieved a higher recall with the UNET. And while many foundation model studies focus on limited geographic regions or hand-curated scenes, FloodNet spans 85 real flood events across all continents, which allowed us to generalize under global variability. And last but not least, I would, I guess, join others in saying that I believe there is a need for paradigm shift from technology or modern model-centric to more impact-driven applications when it comes to geospatial foundation models, such as downstream tasks, such as flood mapping. So similar to the deep learning trajectory in 2016, we've seen a lot of incremental improvements in geospatial foundation models, but relatively limited consideration for their societal, environmental, and economic impact, and I guess real life applications such as global flood mapping. So in terms of next steps for us, a key next step is partnering with end user organizations who need reliable and scalable flood maps that generalize globally. So if anyone here is interested in co-developing or piloting some of these tools, I would be really happy to connect. You have my email address here, a QR code that leads you to my lab page. And I believe that's it. Thank you very much.
Thank you so much, Mirela. That was a great presentation. Much appreciated. Let's see, I should have said this at the beginning, but if you have questions, please post them in the chat, and we have 4 or 5 minutes or something to discuss those questions. So luckily, Mohammed already put a question there. And let's see, Mohammed is wondering whether the accuracy and precision and recall apply to the whole flood extent or to random pixels.
It applied to the whole flood extent, yes, yes.
Okay. And while other questions might still come in, Mirela, I had at the beginning of your presentation, you showed kind of that you were using multiple imageries to capture a flood event, right? And I'm wondering actually what you do when you see on one set of say modus or lens set you don't see the flood, but on another one you do. How do you make the decision of, okay, we're just capturing all the flood events, doesn't matter if it's only on one sensor or multiple sensors, or if you have some sort of a schema in place to determine if, to incorporate a flood
right,
event.
Yeah. So I mean, I would pick the one that's closest to the peak of the flood event. So so if we can capture it with, say, Sentinel-1, that's what I would pick. If we can capture it with Sentinel-2, I would pick that. In our results so far, we found that Sentinel-2 was, for example, more accurate when we had data. So optical data was accurate. However, we didn't always have optical data. So whenever we have Sentinel-1 data, we use Sentinel-1 data. So basically, we use what we can, and we do an accuracy assessment per sensor and try to incorporate that when we make those maps. But we use what we can, because I guess the best thing that you can do is capture the flood event. That's the most important part.
Okay, thank you for that. I see another question from Ken. How would you see the interface between the physical impact model and on-the-ground social impact?
How would I see can you repeat, sorry?
How would you see the interface between the physical impact model and on-the-ground social impact?
Right. So I guess maybe I don't know if I fully understand the question, but basically with our flat maps, we can use any sort of ground data. So we sometimes use social media data, which is of course not perfect. Ground data can be useful for accuracy assessment. In the work that we did with the community in Georgia, we had a lot of points that came from the community. So we use those points for both training as well as validation. So we do rely a lot on ground data. However, doing this globally is really not that practical. So we do use other data sets, other satellite data sets for accuracy assessment. And I guess the physical models, we do have one of the PhD students in my lab is using hand-based flood extents and comparing them with satellite data. And so far, they do not agree very well, but that's more to come.
Thank you. Then there's a question from Beth. Let's see. Were you able to reproduce the really high UNet results on Sentinel-1 Flood 11 for TerraMind? We tried and could not, so it makes me question if that result they published is correct or reproducible.
Right. So we didn't do this just on the Sen1 Floods 11. We did this on FloodsNet, but that's definitely something that we could try to do. So with doing this on FloodsNet, we did find a higher recall than with the four configurations of the TerraMind. But we didn't do this just on Sen1 Floods 11. But it sounds like we should try that.
Thank you. So one more question. There are a few more questions in the chat. So Mirela, if you can answer those
in the chat.
In the chat, that would be great. I'm gonna read out one more. Hi, thank you very much for this great presentation. I would like to ask about Flood Event Archive. I see you used the DFO and EMDAT data, but only till 2020. Do you by chance know some more recent or ongoing global flood archives?
Right, so MDAT is the one to use now. So unfortunately, DFO is no longer, I guess, funded. We still had things such as the size of the flood event and the location of the flood event. So we tried to do a bit of an analysis to try to get to the extent by using a DEM and using the equivalent of HUCs, so watersheds globally, to still use the DFO data past 2020. But yeah, we relied a lot on MDAT and Copernicus emergency services, which still give us polygons of floods.
Thank you, Mirela. And just to, since I know a little bit about this, since I'm leading the DFO Flood Observatory, we currently are not keeping track of floods and updating our list. I hope in the future to do that again, but there will be a gap of, I don't know, 3-4 years or something. But I'm thinking about picking this up again January onwards. So
that would be amazing. That would be amazing. So thank you for
you.
trying to do that, because that's really critical.